Okay, so let's start. So my name is Carlos Rivera. For those who are new to this series of FEFLOW monthly webinars, and this month's topic is related to density effects in groundwater, which cover a variety of applications from seawater intrusion in coastal aquifers to brine environment, lithium mining, and others. So as usual, I will start the webinar with some announcements. Then we will give a quick introduction for those new to the software, and then we focus on the part of the modeling density-driven flow, some application cases where this is needed. I will do a quick FEFLOW demonstration. Okay, so before we start, I would like to mention that we are really coming to a new release. So it's almost end of the year, and DHI best timing is November because we have major releases. So this time we have FEFLOW A1 coming soon. So we will have a release webinar, a special release webinar in November. We have two webinars. So one is the monthly thematic webinar, and the second will be about the release. In this webinar, in this release webinar, or in this release, FEFLOW A1, we have really a number of new features from very exciting new CAD integrations where you can import a number of DXF files, but also DWG files. This is very new for us. So we keep extending the way how well the well manager is working, implemented some rules and grouping. There are a lot of changes and improvement for geothermal applications. So if you are working in this sector, please come to the webinar. You will be very surprised about what is possible now in FEFLOW A1. We changed the way how the observation point dialog works in FEFLOW. We expanded this for a number of possibilities to control budget groups, content groups, and also directly apply the information into FIPES. And we have a lot of number of changes and improvements in Python. So we will bring a new package called Python or PySMH, which stands for Python Supermesh. And with this package, you will be able to build from scratch 3D super meshes, run mesh generators, build 3D models, and run the simulations. So everything in one single Python script. So really, it's something really, really promising because it's the first time that you are capable to build an entire FEFLOW model from the very beginning until the end with one single script. And we have also a number of new 3D super mesh tools supporting the development that we are doing in 3D meshes in FEFLOW, which started already with a 0 version. For those new to the session of this webinar, so we will be talking about FEFLOW. So FEFLOW is part of the mic modeling software and family. DHI is responsible of developing these softwares. We have been doing this since a number of years. We basically have a product for every single part of the water cycle, from groundwater today with FEFLOW, but also wastewater treatment plants, my urban, so urban water systems, catchment hydrology, my SHE, surface water, and 2D hydrodynamics, my 21, or my 3 in the case of 3D, integrated river water resources management with my hydro basin, and so on. So FEFLOW has been already for a while, since the late 70s. It's a finite element designed for contaminant flow, groundwater age, heat transport under saturated and variable saturated conditions. Just an overview for those who are new. So we released the first version of FEFLOW in the late 70s, and DHI is very actively developing FEFLOW with 2 releases every year. Our current release is A0. November will come with A1 release. Few details about what is FEFLOW. So our major concept is all-in-one solution, and this is what we are trying to develop and to provide through all the different releases. So you have one tool to do a number of applications, so you don't need to care in looking packages or into exchanging data from one package to the other, because we always release a full package of the software for flow, mass, and heat. Save time and boost efficiency through a number of workflows. I just mentioned what is coming next in A1. So we extend the programming interface. So this is something very very powerful in FEFLOW, but we also have methods of different import-export of multiple file formats, interoperability with geological models, and so on. And our third core is stencil visualization. So there is no other groundwater software in the market who has a better visualization than FEFLOW in 2D or 3D. So FEFLOW is typically we talk about groundwater for FEFLOW. We connected, but it's really more than that because we are have been working in subsurface flow and transport for a number of years. And today's presentation will be related to density affected flow. So this is what we will be doing, which can be also connected sometimes with chemical reactions. So you can have a number of chemical species who are also affecting the density, and then incorporate this into a FEFLOW context. And to start, one last slide about this introduction. Other of the key components of the software is the flexibility, how we create finite element meshes, so in 2D and 3D, interacted with geological maps or geological models to build an structure meshes or a combination of these. Okay, so today's presentation is about density-driven flow, or density-dependent flow is also called. And there are a number of applications where it's really relevant to use, and we should do it because otherwise our modeling calculations will not properly represent the physical processes. So when we talk about density-driven flow, the first case that it comes to our mind is saltwater intrusion or seawater intrusion in coastal aquifers. So you have a typical freshwater aquifer and you have the sea level, and there is an intrusion of the sea into the coastal line, and there is a certain equilibrium between fresh water and salt water, and depending on human activity, this equilibrium could be breaked. So if you have pumps around this in this freshwater aquifer, so the equilibrium will be broken and there will be more intrusion. Upcoming, this could be a number of applications. So I see some of you are working in mining, recognizing some of the names. So this could be a brine. So you have a brine, so a mine, lithium mine, and then there is a salt accumulated in the lower part of the reservoir, and due to density changes, so you have a movement from salt water to fresh water. And if there is a pump, because you are extracting the mineral from the aquifer, you are also enhancing this propagation of the salt water, so enhancing the upcoming stratification boundary layers flashing, so you can have fresh water and salt water. This could be a number of applications if you mine an island which is surrounded by the sea, so you have salt water on the bottom, but still you could have some freshwater aquifers or freshwater lenses, so you can have such a stratification here in the system. We also have cases where you have different solids with different densities, which can be mixed and can be also simulated in FEFLOW. Or you have cases where you have a sol being located in the upper parts of the domain. Some of you might work in the geothermal sector, so this also could be related, or there are applications where density-dependent flow is related, especially for middle depth to deep geothermal applications where there is a geothermal gradient, so density change also with temperature. You are pumping, so you are recirculating if this is an open loop. You are changing the conditions of the system, so you are mixing the water. And this could also is necessarily to be simulated with the density. Underground nuclear engineering, so nuclear repositories. So this is a very important topic in multiple countries. So also these are deep underground, subjected to different heat sources, density change because of the heat, and others. And there are a number of other applications of salinization of soils, or due to irrigation processes, or drying conditions in materials, thermal isolations, etc. So from the very beginning, when FEFLOW was introduced in the late 70s by Professor Dish, so there was a major focus of the solver was to really try to solve these problems of density-driven flow because they are very complex numerically. It's not easy to solve, so they're subjected to small of number of details in the implementations. So FEFLOW has been well benchmarked. So I put here the list of the different benchmarks which are available in white papers of FIFLO books. In case you are interested on those, just please review it this. So there are a number of very famous benchmarks like the Henry problem. So it's like everyone who is doing density-driven flow knows this problem and has been used for a number of applications and software, or the ELDA problem, where you have salt water or heavy water located on the upper part of the domain, and then the rest of the domain is fresh. There are no external forces like hydraulic gradients, and due to the changes of density, there will be a propagation, this fingering of this salt plume. Or the typical case of a salt plume is also being benchmarked. So how is this being done in FIFLOW? So we have multiple levels of coupling. So when we say density-driven flow, we start introducing the new terminology called coupling, flow, and mass equations, mass transport equations. So normally what happens in every flow and mass transport is you solve the flow equation first, and then in the next, the mass transport equation within the same time step. Then you go forward to the next step, and again comes the flow equation and the mass transport equation. Now we are saying, okay, there is a density effect, so we need to couple, and they need to be coupled because the density term participates in multiple equations. So you you can see it here through the Darcy law. So you have the the conductivity tensor, which also there is depends on some viscosity, gravity, density, and permeability. So the density is going to affect Darcy law, or in different levels of equations. So when we say couple, so we are basically iterating again and again the flow and the mass equation within the same time step. And that is numerically expensive. It takes more time to calculate a flow and mass problem with density than the one without density effects. Then the equation or the coupling could be considered in multiple levels. So we have something what is called density variation. So the most simple and most common is the so-called Boussinesq approximation that I'm going to explain later, where you only have gravity-related terms applied to the system. But you can also have gradients or rate change of terms, or all the full expansion, so gradient rate of change of fluid dispersive terms. So I'm gonna focus most in the presentation to the first point because it's most of the commons is mainly used. If you're interested in these two other topics, so you can send me an email, or I will recommend you to take a look on the FIFLO book, on the FIFLO white papers. So also one thing that not many users know, because typically you do a mass transport problem with one individual chemical species, but FIFLO also support multi-species transport. So the equation that you see here, the second one is the advection, dispersion, diffusion equation. So this one will be solved for each individual mass transport species. And you can also say, I would like to include density-dependent processes. Okay, I have a system which is simulating chloride and maybe sodium or magnesium or any other ion. You can tell FIFLOW, okay, look the concentration of each of these individual species, and then sum up the mass and use this mass to update the changes of density. That is also supported and is referred here as a density ratio depending on multiple species. So to start, so we need to put at least a number of equations, otherwise I cannot continue speaking. So I try to keep it simple because of the time. So we have Darcy law, That is my Q, so Darcy flux. Conductivity, that's a fancy way to write the hydraulic gradient. So we have a pressure a pressure head, and then we have a gravitational heads, so the sets. Here it comes this term called buoyancy term, which is introduced as a change of density. This is the density of the, depending on the X concentration, minus a reference density. If we come back to the topic or to the example of a coastal aquifer, this will be the density of fresh water, the freshwater aquifer, let's say 1,000 kilograms per cubic meter, and divided by the reference density. So the job here is, how do we get this part in red? So we approximate this by the following. There are two terms depending whether you work in the water quality part doing mass transport, or you work in the geothermal part doing heat transport, or maybe you work in both systems. So for the first part, it's called density ratio. Then there is a change, C minus C0. C is the concentration bill calculated in FEFLOW in each node. C0 is the concentration of fresh water. Cs is the maximum concentration, let's say salt water, minus C0. So you have a factor to tell which tells FEFLOW what will be the delta of density if my concentration increase or decrease. Then you are doing now geothermal projects, so you have expansion coefficient beta, and this is multiplies a change of temperature. T is the calculated temperature. So if we are doing middle depth geothermal application, let's say 70, 80 degrees, will be 70, 80 degrees minus the reference temperature in the system. So you have a change of density as a function of C and as a function of T. There is a plugin called Beta Gamma, which allows also to extend this equation by introducing changes due to pressure. Because if you are, back to the case of deep geothermal, if you are insisted with a high pressure, so the equation of states, which define this density and all the other terms, will also depend on pressure and needs to be considered. So if you are working in that level, so there is a potential to use a plugin for applying this. So how do we solve it is with this simple linear model. So basically, I am talking all the time about density, but FEFLOW does not really solve density. So FEFLOW solve or takes into account a relative change of density, but it doesn't really look exactly what is the absolute values of density. So this is a quite nice trick to simplify the calculations and make it more appropriate. So you see here the screen, so there is a linearization of a density, so vertical axis by horizontal axis concentration. We need, in terms of parameters, density ratio, and the minimum and the maximum concentration. With these three values, it doesn't matter which concentration you are, we will know which is the density or is the relative change of density applied to that concentration. So this density ratio is very simple calculated. So you need to know the density of your min and maximum scenario. So let's say salt water 1024, fresh water 1000 divided by 1000, then you have a 0.0245 density ratio. So that is what is used. If you are working with other types of fluids or brine or hypersalines environments, so then you need to really take the correct density and then just calculate in the similar manner the density ratio for FEFLOW. In the case of heat, we have other expression, which is a polynomial function of density. So there is a function already implemented in FEFLOW. You can come and modify this polynomial expression if you wish. It's a six-order polynomial, which indicates the changes of fluid density from a range from 0 to 100 degrees. If you want to go in another range, so you need to adjust this polynomial expression. So we were saying there are different levels of introducing this or considering density-driven flow in FEFLOW. And I was mentioning at the beginning, okay, this definition called Boussinesq approximation. So it's a complex mathematical term, but to explain it, I have this simple example. Imagine you have a simple aquifer. So this is a confined aquifer, and in this confined aquifer, you have an injection. You are injecting a fluid on the left side of the aquifer. On the right side, there is an outlet with a hydraulic head of -1. So the gradient is very simple from left to right, so easy to solve. And what is happening to make it more interesting? So we are applying also a heat transport problem into the system. So the temperature that is coming here is 10 degrees. It comes cold water. We inject cold water into the aquifer. Cold water comes all the way, and then before it reach the outlet, on purpose, I heat up the water with a temperature of 90 degrees. So before reach the outlet, we heat up the system with 90 degrees. So therefore, the rest also will equilibrate to 90 degrees. So with a Boussinesq approximation means there is no expansion of the fluid volume. So you add a -1. Here was the flux being injected through the well. Then you get a -1 at this point. But if you would like to not consider, so without the Boussinesq approximation, we are accounting for those changes on the fluid volume. So you add 1 cubic meter per day on the left side, but you get more because we account for the change of the expansion of the fluid. So we have a little bit more in this case. So that's a nice slice if you want to understand. So when is necessarily or no, or what does it mean with or without the Boussinesq approximation in FEFLOW. Other things to consider, so FEFLOW works with a so-called freshwater equivalent. So all the equations are calculated as a freshwater. So this means if you set your boundary conditions, if you go to the example of coastal aquifer when you would like to introduce the location of the sea border, so the saltwater head of the sea. So you need to basically use special boundary conditions to ask FEFLOW automatically to convert from saltwater to freshwater equivalents. Otherwise, you could also do it yourself. In the case that you have data, so you are measuring piezometer data in locations with high density, you will need to also correct your measurements by density before you put it into FEFLOW and before you compare scatter plots or do a calibration. Otherwise, you will immediately have already a offset between your measurements and your simulated results. Okay, so there are a number of applications where this can be used. So just give you a few images about this. So salt upcoming. So I was mentioning a few cases about, for example, brine, lithiums. No, you might have here halite sediment, salts, very salt sediments, or so there is a upcoming. So seawater intrusion, that is a coastal line here, so concentration, high concentration, 35 grams per liter. Then there is a well, that's why we have upcoming elongated in this location, and that is the interface between fresh water and salt water. Thermohaline flows, so those ones I see some German colleagues here, so you know this German base in the north, so which is quite popular. A number of publications, so some colleague of us, but also other research scientists. So I say here Fabian Magri, which has tried to simulate this reservoir, this important geothermal reservoir with FEFLOW. And then what you see here, that there are some significant salts. So the salts which will play a role on the geothermal system. No? So you have heights, temperature profiles combined with salts. So you need to have to solve both equations, flow, obviously mass and heat. Then there will be a density depending on the high concentration, but also will depend on the temperature. And these type of problems are called thermohaline simulations. So if you are interested in those, so there are a number of papers that you can find where FEFLOW was used for those applications. Those ones working in mining, so this also FEFLOW is very popular in lithium applications, so it's a lot of demand on this because of the e-mobility around the world. So it's estimates of lithium carbonates. So typically you have so this is a case in South America where you have a lake, so Salt Lake, then you have some lateral recharge, maybe come from the mountains. You have also normal groundwater flow. The evaporation rate is very high. It's really is hyper-arid environment, so 1,000 millimeters per year of evaporation or even more. So it's a significant accumulation of salt. So there are some crusts being accumulated in the surface. So you need to incorporate these density changes here. Um, Other things that are always asked, and I just put it here, so, okay, especially for that case of the salar, so because we are talking about evaporation, so people like to simulate evaporation depending on depth of saturation or groundwater extinction depth is also called. So which means that you can have a evaporation rate depending, changing or decreasing exponentially or linear as you want to implement it on the depth to groundwater. And this can also change to a number of densities. So I forgot to put the publication here, but this is also a image from the Salar de Atacama in Chile. And this can be also simulated in FEFLOW. So I don't know if I can press here. Yeah, this is a short video for demonstration purposes where you see in the lower part of the domain there is a high concentration, it's 100 milligrams per liter of something salt or heavier, and then it's evaporation source of flux on the top. So if you model with FEFLOW, you will expect to see this redistribution of the mass from the lower part of the domain into the upper part. So you can see here is that the also the concentration will rise because you are evaporating fluid, so you are reducing the volume, but the mass is still staying in the system. So then you need to know until what point is admissible, because in reality it will not continually all the time to increase the concentration, so you will have also some saturation, so it will precipitate, and this can be also modeled. So in this example, I'm using a Python script to control some of the evaporation fluxes. Okay, so with this, I would like to jump to the live demonstration, and for that, I prepared very simple example. So what we are doing is, this example is, we have only one model. When we in this model, we have a salt pool on the top, and then we will try 3 different scenarios. And with the 3 different scenarios, I would like to test whether it's important or not to implement density-driven flow in the system. So you see this equation, this is again Darcy law, and then you need to ask yourself, if you want to implement density-driven flow in the system, which of the dominated forces in this equation? So we have better pressure or forces, so it's a strong hydraulic gradient. So maybe it's not needed. Maybe it will be blurry. The signal of the density will be blurry by the difference of pressure. Maybe it's the other way around. So maybe there is no flow, and most of the movement will be depending on the pressure, or maybe there is something in between. And this is what we try to do in this exercise. So let me open this in FEFLOW 8, still for now. Okay, so the case that we are doing, so before this, we start with a 0 concentration. So I will go to Edit, Problem Settings quickly to show you what is it about. So it's a cross-sectional model. It's very simple for time being. So saturated, we have a mass transport, a steady state flow, and transient for the mass transport. The simulation runs for long time because this process is really density-driven processes takes a while to equilibrate. So you run it for a long time, and I use a first-order accurate because it's It's a better approximation for the time steps for these heavily calculations of density-driven flow. Sometimes, depending on the type of model, you need to control the time steps, say to reduce the time steps to maintain the equilibrium. And then transport settings, so we solve the typical convective form, fluid density again, Boussinesq, and then we have here reference value. These are the two values that we were seeing in the equation, so the C0 and the CS, so the maximum 100 milligrams per liter. And what else I need is a set of boundary conditions. So in this first example, there will be no flow, only density. Or we will let's run it without density and then with density, but no hydraulic gradient. So this basically one single node having the same initial value and initial conditions. And in terms of the mass transport, I have here a salt pool with a fixed concentration all the time. So let me, this is the density, this is the third parameter you need. So let me set this one back to 0. 0 means that two equations are solved independently, so they will not be coupled. And now we run it. It will ask me to save. No, I don't want to save it. And now we will see what is happening. So it's something very simple. There is no gradient, so we have only the plume basically near to the location of where the boundary condition is, and the plume is moved or driven only by diffusion and dispersivity. Yeah, there is no advective part here. Okay, so let me reopen this, and now see the density is 0.01. So I'm telling that there is 10% more. When I have the maximum concentration, I have 10% more density than the reference concentration of 0. Now, if we start the simulation, you will see that it takes a bit more time to calculate. So if I look the time steps, so FEFLOW needs to decrease the time steps. FEFLOW needs to decrease the time steps to keep the accuracy. It will take a few seconds more to finish. And then you see that the picture of the distribution of the concentration is totally different to the previous case. So meanwhile is running, so I use the time to start answering some of the questions. Okay, so Dave is asking whether we will have a sales-based course about this. Yeah, so this is a good idea. So we haven't planned it, but I think will be relevant for everyone. So we can do that. And then there are a number of questions here. I'm doing a seawater intrusion modeling using FEFLOW 8. At the moment, I have several questions. Okay, in the sea level rise simulation for mass boundary condition at the coastal boundary, should I assign a mass VC of first type or second type? I mean, if you know the concentration, you will assign a first kind boundary condition equal to the concentration of the seawater. It is correct if I assign a first time hydraulic head times series changing at the coastal boundary to simulate the sea level rise. It is correct, but you need to remember that FEFLOW works with seawater, freshwater equivalent, so your concentrations needs to be, or your heads needs to be corrected by density. And to simulate brine water injection to a multi-layer well, which type of BC, and you need a mass concentration BC as well. Thus, the student license will receive an update of A1. You need to request it. I mean, it's not automatically, but since you are a student, so you can also update your license without problem. Okay, so that's part of that's the simulation. And now let's try to introduce, sorry, me answer live, so I mark it. Another case, in the second case, we have the following. So we are now, it's the very same example. And in this example, what we are doing is we have a gradient this time. And we have a gradient with a value, or the head is 0, and in the other side is 0.1. The distance of the box, if I remember correctly, is 100 meters. Okay, so is 0.1 divided by 100 meters. That is the hydraulic gradient that we are applying in the system. The rest of the information is the same. So we just see what happened when we apply a hydraulic head gradient into the concentration, into the problem. So what is now happening is the concentration basically just got is completely flashed because the gradient is strong, and the pressure forces are winning to the to the buoyancy term. So there is not much of concentration going. And let's do one last case where we try to, let's say, make the two forces not identically, but reduce the gradient. So if I look here, we have 10 times less, 0.01 divided by 100 meters. That will be the hydraulic gradient. And if I run the simulation, now start again the propagation due to density, but then there is certain gradient, so the concentration would also be and doesn't change. So with these three cases, so you can really see what is the effect of having only this part. So this was in the first one, or having this part more strong, or having the two of them equally combined. So the take-home message of this webinar basically is, so you need to model density-driven flow in some cases, but you need to evaluate whether it's necessarily, because the effort of doing this type of process is time consuming in terms of numerical calculations. So you need to also improve meshes. So a mesh that is running for flow might not necessarily run for mass. And if you put on top density, you might even have to refine it more. So you need to basically evaluate this. So you can easily estimate in a paper. So if you know what are the density values that you expect, you know this term already. And if you know the hydraulic gradients or that you spec in the system, you also could know this part. So you can try to calculate whether this one will be significantly lighter than this, or both equally, and then decide whether it's relevant or not. Otherwise, you can also do trial and error and implement with or without density in FEFLOW. Okay, and since there was a person asking a lot about this seawater intrusion, so I had here prepared another model, which is the one that we're using our official FEFLOW standard training. So here you can see what is the name of the student, Devandra. So the way it's a 2D model with a constant head of 0 corresponding to the seawater. Then there is also a recharge on top, fresh water on the left, also fresh water, and concentration being fixed, salt water with a value of 35,000 milligrams per liter, and on the top fresh water with 0 milligrams per liter. Using a density ratio as it was calculated in the presentation, salt water minus seawater density divided by fresh water density. Salt water minus fresh water divided by fresh water will be that value. Just to here, then let me put this one to because the concentration is also changing during time. It's also here, you will expect, you need to expect numerical oscillations. So the question is how large are them? So this is something that you need to review. So the simulation starts like this in time 0, where we assume there is already a high concentration in this triangle, and then there are no uh, pumping or other anthropogenic activities that could modify the the interface between fresh water and salt water. But if we then you can move to the final simulation time, and this will be basically the equilibrium. So depending on your water quality norms, or some um, countries decide or define that that 1,000 milligrams of concentration could be a good threshold to of TDS, so total dissolved solids. Could be a good value for implementing a reference line between fresh water and salt water. So I will like to thank you for participating in this webinar, and please don't forget to register for the release webinar the 30th of November at 3 p.m. so UTC time. And I hope to see you the next month in the next set of webinars. Have a good day, good afternoon, until the next time. Bye.